Somewhere above the Pacific Ocean, at an altitude of roughly 400,000 feet, that's 75 miles above the surface of the Earth, where 4 human beings simply disappear. They don't die. They don't stop existing. They just become, for a stretch of time that lasts about 6 minutes, completely unreachable. No signal. No voice. No confirmation that anything is still okay. Mission control goes quiet. The families in the viewing room hold their breath. And somewhere up there, inside a capsule roughly the size of a large SUV, 4 people who have just flown around the moon are hurtling toward the ground at over 24,000 miles an hour, with nothing between them and vaporization but a 16.5-foot disk of material that engineers had been quietly worried about for more than 3 years. What I keep coming back to, and I've thought about this a lot since following the Artemis II mission closely, is that the scariest part of going to space has never been the launch. It's always been the return. Artemis II launched on April 1, 2026, from Kennedy Space Center in Florida. The SLS rocket, NASA's most powerful launch vehicle since the Saturn V, lifted off at 6:35 in the evening carrying Wiseman, Glover, Koch, and Hansen into a trajectory that would take them farther from Earth than any human being has traveled in over 50 years. At its farthest, their capsule, named Integrity by the crew, reached a distance of 252,756 miles from Earth, about 4,105 miles beyond Apollo 13. They had beaten a record that had stood since 1970. But records on the way out are one thing. The record that mattered, the one that actually defined whether this mission would end in triumph or something far more terrible, was the speed at which they would return. 24,661 miles per hour. Fast enough to cross the continental United States in roughly 7 minutes. Fast enough to turn air itself into a weapon. To understand why those final minutes were so consequential, you have to understand what happens when something moving that fast meets air. In everyday life, air is essentially nothing. It moves through your fingers when you wave your hand. It barely registers. But at 25,000 miles an hour, air doesn't have time to move. The capsule hits it faster than the molecules can get out of the way, and what happens next is a kind of violent compression physics doesn't usually show us. The air doesn't just heat up, it transforms. It becomes plasma. Not the kind you learn about in a high school chemistry class as the forgotten fourth state of matter, but actual ionized gas, glowing, electrically charged, reaching temperatures of about 5,000 degrees Fahrenheit on the exterior of the heat shield. Half as hot as the visible surface of the sun. Against that, the entire engineering ambition of the Orion capsule's heat shield is pointed. The material doing this work is called of coat. It's an ablative compound, meaning it's designed not to resist heat but to absorb it and char away gradually, carrying that thermal energy with it as it erodes. Think of it like a controlled sacrifice. The outer layer burns so the inner layers, and the crew behind them, don't have to. It's elegant physics, in a grim sort of way. But after the uncrewed Artemis I test flight in late 2022, something was wrong. When engineers inspected the heat shield after recovery, they found unexpected cracking. The of coat hadn't eroded the way the models predicted. Instead of charring away smoothly, chunks of it had blown off, leaving behind pockmarks and voids that nobody had seen in ground testing. NASA's Office of Inspector General later noted that engineers had identified more than 100 locations where the ablative material had worn away differently than expected. And the problem wasn't obvious at first. It took nearly 2 years of painstaking investigation, including replication tests at NASA's Ames Research Center in California, before engineers found the root cause. It came down to something almost counterintuitive. The of coat couldn't breathe. Artemis I had used what's called a skip reentry, a trajectory that sends the capsule dipping briefly into the upper atmosphere, like a stone skipping off the surface of a lake, before pulling back up and making a second, final descent. It was designed to improve landing precision and reduce peak heating. But the skip introduced a thermal trap that nobody had fully anticipated. During that first dip into the atmosphere, the outer char layer of the coat heated up and became permeable. That's normal. That's what it's supposed to do. Let gases generated by the pyrolysis process inside the material vent outward. But when the capsule skipped back up and external temperatures dropped, the outer layer cooled and stiffened. It became less permeable again. The internal layers, though, were still extremely hot. Still generating gas through pyrolysis, a slow chemical combustion that doesn't even require oxygen. All that pressure had nowhere to go. So it went through the only path available, outward, violently, fracturing the char and blowing it away in fragments. The coat used in the Artemis heat shields, it turned out, had been slightly reformulated from the original Apollo-era version. And that reformulation had changed its permeability in ways that nobody caught before flight. Here's the part that makes this feel genuinely heavy. By the time all of this was understood, the heat shield for Artemis II was already installed on the capsule. Replacing it would have taken 18 months or more. And so a decision was made. One of those decisions that rarely makes headlines but carries the full weight of what it means to do this kind of work, to fly anyway. NASA spent years running simulations, testing at Ames, convening independent review teams, and in January 2026, NASA Administrator Jared Isaacman brought engineers, outside experts, and even members of the press together to go through the data. They modeled what would happen if large sections of the heat shield failed completely. The conclusion was that Orion's thick composite base, reinforced with a titanium framework, could keep the crew safe even if the coat were entirely stripped away in some areas. The fix, in the end, wasn't a new shield. It was a new trajectory. Instead of the skip Reentry, engineers designed a steeper, more direct descent for Artemis II, one that would sustain higher external heating throughout and keep the outer char layer permeable the whole time, letting gas escape continuously rather than trapping it. The trade-off was a narrower landing zone and slightly higher sustained thermal stress. But it would eliminate the specific failure mode that had broken Artemis I's shield. There's a philosophical tradition in existentialist thought. Kierkegaard called it the leap of faith, the moment when reason runs out and you act anyway. When you've gathered all available information, done all the work, and then you let go and trust something larger than certainty. Every astronaut who has ever strapped into a rocket has made that leap. But Artemis II made it at a moment when the specific hardware in question had already shown it could fail. That's not recklessness. That's something older and harder. That's the oldest human calculation there is. The odds are acceptable, the mission matters, and we go. On April 10, 2026, at 7:33 in the evening Eastern Time, the Orion capsule separated from its service module above the Pacific. The service module, the cylindrical section that had powered and sustained the crew through 9 days of deep space travel, peeled away and began its own descent into the atmosphere, where it burned up harmlessly over open ocean. The crew module, alone now, thrusters firing for 19 seconds to adjust angle and attitude, pointed its heat shield toward Earth. What happens next is almost meditative in its precision. The capsule is descending through a sequence that has been rehearsed in simulation thousands of times but has only been attempted once before with human beings aboard, and that was Apollo 17, in December of 1972. At 7:37 p.m., a brief burn adjusted Orion's orientation. Everything tucked and sealed. Suits checked for leaks, all clear. The crew, suited up and strapped in, began feeling the first subtle increases in gravitational force. After 9 days in microgravity, gravity's return is felt not just as weight but as strangeness, a reminder that the human body's default state is not floating. At 7:53 p.m., Orion hit the upper atmosphere at 400,000 feet. traveling at roughly 24,000 miles per hour. Within 24 seconds, the plasma had formed. The electromagnetic interference from ionized gas surrounding the capsule severed radio contact with mission control. The screens at Johnson Space Center in Houston went quiet. Flight Director Jeff Radigan had spoken publicly about anticipating what he called an irrational fear, an acknowledgement that even the most technically precise human minds still feel, in those 6 minutes, what the rest of us would feel. The families in the viewing room sat together. Outside, the recovery ship USS John P. Murtha waited in the Pacific, about 2,000 yards from the targeted splashdown point, engines idling. Inside the capsule, the temperature at the heat shield's surface climbed. 1 minute and 22 seconds into the descent, at peak heating, the exterior reached approximately 5,000 degrees Fahrenheit. That number is difficult to hold in the mind. The temperature at the surface of the Sun, the visible photosphere, is about 10,000 degrees Fahrenheit. The Orion heat shield was experiencing roughly half that. Sustained. For several minutes. Inside the crew compartment, the temperature remained comfortable. That's what the heat shield is for. But the crew was experiencing something else, up to 3.9 g of deceleration. Nearly 4 times their body weight pressing them into their seats as the atmosphere steadily scrubbed away the capsule's velocity. At 3.9 g, lifting your arm requires real effort. Breathing takes more work than it should. Everything becomes heavier. What I keep returning to, thinking about those 6 minutes, is the quality of the silence on both ends. In Houston, engineers watched data streams that were still arriving, thermal readings, accelerometer data transmitted in the microseconds before plasma fully closed the signal window, trying to infer in real time what was happening to a vehicle they could no longer reach. And inside the capsule, 4 people who had seen the moon up close, who had watched a solar eclipse from 252,000 miles out, sat in the particular silence of people who have done everything they could and are now simply waiting. At approximately 7:59 p.m., 6 minutes after blackout began, Orion emerged. The plasma thinned. The signal returned. And the first words from the crew came through to mission control. "We have you loud and clear." The response from Houston's White Flight Control Room, that particular room where families and mission controllers had been sitting together through the silence, was the kind of sound that doesn't quite translate in a description. It was relief at a frequency that's physical. But the work wasn't done. The capsule was still descending at around 9,000 miles per hour. Still less than 200 miles from the splashdown target. 8 minutes after atmospheric entry, Orion passed through 100,000 feet. 1 minute later, it broke through the sound barrier, going down, not up, slowing through Mach 1 toward the ocean below. Then the parachute sequence began. At 23,400 feet, the drogue chutes deployed, small stabilizing parachutes designed to slow and steady the capsule before the main chutes could safely open. Orion's velocity dropped to 479 feet per second. At 5,400 feet, the drogues were cut. At 6,000 feet, the 3 main parachutes unfurled, each one designed to be part of a system of 11 total chutes, working together to slow a 16,000-pound capsule from nearly 300 miles per hour to something approaching 20 miles per hour. It takes extraordinary engineering to turn the violence of Reentry into a gentle landing. The parachutes are part of it. But so is the sequence, the timing between each deployment, the angles, the load distribution across the canopy lines, all of it calculated to manage forces that, if mistimed by even seconds, could catastrophically damage the vehicle or the crew. At 8:07 p.m. Eastern Time, on April 10, 2026, the Orion crew module touched the Pacific Ocean at approximately 20 miles per hour. Off the coast of San Diego, exactly where the revised trajectory had aimed it. The mission had lasted 9 days, 1 hour, and 31 minutes. The crew had traveled an estimated 694,481 miles. They had broken the record for the farthest distance from Earth a human being had ever reached. They had watched the moon from 4,070 miles away, close enough to see craters in detail, to name them, to feel their scale. Jeremy Hansen, the Canadian astronaut, had suggested naming a bright lunar crater after the late wife of Commander Reid Wiseman. The crater, now called Peril, is visible on the moon's surface at the 10 o'clock position of the Oriental Basin. I find that detail extraordinary. That in the middle of a mission defined by engineering problems and calculated risks, there was still room for grief, for love, for the deeply human act of naming something permanent in honor of someone gone. Space has always done that to people, made the personal feel cosmic, made the private feel historical. Within about an hour of splashdown, Navy divers had attached stabilizing equipment to the floating capsule. The front porch, an inflatable raft, was positioned beneath the side hatch. Koch was extracted first, then Glover, then Hansen, then Wiseman. All four walked with minimal assistance to the ship's medical bay aboard USS John P. Murtha. NASA Administrator Jared Isaacman met them on the flight deck. The heat shield was recovered with the capsule. Engineers would now do what engineers always do after a mission like this: inspect, measure, compare predictions to reality, look for places where the models were wrong. For Artemis II, NASA has already committed to a redesigned shield that addresses the of-coat permeability problem. The lessons from both Artemis I and Artemis II are being written into the hardware that the next crew will trust their lives to. That's how this works. Every mission is, in part, a test. And every test produces data that the next mission uses to be slightly less likely to fail. Progress in space has never been a clean upward line. It's always been a series of near misses and corrections, of engineers staying up through the night to understand what went wrong and how to make it less likely to go wrong again. There's a philosophical question embedded somewhere in all of this that I think about often. What does it mean to accept risk on behalf of others? The engineers who signed off on flying Artemis II with an imperfect heat shield, they weren't the ones strapped into the seats. The managers who made the call to proceed, they went home afterward and had dinner. And yet the crew, knowing all of this, chose to go. Glover said he'd been thinking about Reentry since the day they were assigned. Wiseman said after splashdown that he hoped the world might pause for just a moment and remember that this is a beautiful planet and a very special place, that we should cherish what we have been gifted. That last part catches me. The farthest from Earth that humans have been since Apollo, and what comes back with them is not conquest but gratitude. The overview effect, the cognitive shift that astronauts often describe after seeing the Earth from deep space, this sudden clarity about how fragile and singular and irreplaceable it all is, seems to have been alive and present in this crew throughout. Christina Koch, looking out of Orion's window at Earth on April 4th, took photographs that circulated widely in the days after the mission. The Earth, in those images, is small enough to hold in one hand. Blue and cloud-streaked and alone against an absolute darkness that has no bottom. 50 years ago, the last humans to leave Earth orbit came home in Apollo 17, and then nobody went back. Not because we didn't want to. Not because the technology stopped working. But because the will, the funding, the political alignment, all of that drifted. And for half a century, everything beyond low Earth orbit remained untouched. What Artemis II did was re-establish a fact that had faded almost into mythology. That human beings can leave the neighborhood of Earth, travel to the vicinity of the moon, and come home. That it is possible. That the physics works. That people are willing to accept the risk. The 13 minutes of Reentry, from service module separation to splashdown, were not just an engineering milestone. They were a kind of proof. That a heat shield holding together under conditions half as hot as the sun's surface while 4 people sit inside and wait is achievable. That we can do this. When I think about those 6 minutes of silence, the blackout, the plasma, the moment when mission control had no way to know what was happening inside that capsule, I keep arriving at the same thought. Not about technology. Not about engineering. About something simpler. There's a version of human courage that shows up in enormous moments. The launch pad, the lunar flyby, the heat shield glowing at 5,000 degrees. But there's another version, quieter and maybe harder, that shows up in the 6 minutes when there's nothing left to do. When you've run the calculations, reviewed the data, made the decision, and now you're simply in the middle of it. No controls to adjust. No checklists to complete. Just you, and the mathematics, and the dark. Wiseman, Glover, Koch, Hansen, they sat in that dark. And came out the other side. Somewhere above the Pacific, the heat shield did what it was designed to do. The coat charred and eroded and carried the heat away with it. The composite base held. The parachutes deployed in sequence. The ocean was right where the trajectory said it would be. And 4 people who had seen the moon up close came home. Artemis II will carry a different shield. A better one, designed with the knowledge that this mission produced. And whoever sits inside that capsule during their reentry will be slightly safer because of the 13 minutes these 4 people flew through. The darkness between planets is patient. It doesn't care about our deadlines or our politics or our fears. It simply is, vast and cold and ancient beyond our ability to truly comprehend. And against that, we send 4 people in a capsule the size of a living room, with a heat shield made of a material that has to breathe at exactly the right moment. And somehow, again, it worked.